Am I audible to you?
Yes, sir.
Yes, sir.
Actually, in my mail, there was your old link. So by mistake, I have clicked on the old link. So that's why I think I was not able to join you.
Yes,
Fine.
sir. Actually, I have shared on
WhatsApp also. Yeah, fine. So, should we start, or
yes, sir.
you have some
Yes, sir.
formality? You may have some formality of the
Yeah.
program to introduce your participant, something like
Yes,
that.
sir. We will start, sir, and we will invite you, Rajni.
Welcome everyone. Thank you for joining us for the TechCube Third sponsored 1 week FDP on the topic Recent Advances in Composite Materials. My name is Rajni Chaudhary and I'm working as Assistant Professor at Engineering College, Banswara. The webinar is being organized by Department of Mechanical Engineering, Engineering College, Banswara, Rajasthan, under the mentorship of BVM Engineering College, Anand, Gujarat. I now request Principal Sir, Dr. B.L. Gupta Sir, for sharing his thought on this FDP.
Thank you, madam. Myself, Dr. B.L. Gupta, welcome all of you on behalf of Engineering College, Banswara family. A FDP on recent advances in composite material starting today onwards, 21st December to 25th December, on different times. Number of speakers will join us. Dr. A. Seth from SVNIT Surat, Professor G.S. Danay sir from MNIT Jaipur, Dr. M.L. Meena sir from MNIT Jaipur, Dr. Akhleshwar Pandey from Government Engineering College Bharatpur, Dr. Atul Bakri sir from DRDO, Dr. Indra Deep Singh from IIT Roorkee, R.S. Meenaji from MNIT Bhopal, Bhupesh Goyalji from Barodara, and all my head of the departments and coordinators, conveners, and dear participants. This is very useful and recent topic in the composite materials. Hope you will enjoy this FDP for next 5 days and got the benefit. Thank you. And again, I welcome all of you, all of our
Join
participants,
करोगे क्या?
speakers,
बोलोगे?
on behalf of
आ जाओ.
Government Engineering College, Banswara family.
हाँ, कर
Thank
लो.
you.
जल्दी कर.
Thank you,
Thank
sir.
you.
Thank you, sir. Now I request Shubham sir, our TechCube coordinator of Engineering College, Banswara, to share his views on the topic Recent Advances in Composite Material about this FDP.
Thank you, ma'am, for giving me this opportunity to say something about this particular FDP. We have also organized a few faculty development program as well as short-term training program for various students of Rajasthan as well as the countrywide during this pandemic in the online version. And even in the last year, we have organized such kind of activity under the Department of Mechanical Engineering as a name of RECT in the recent advances of cutting fluid technologies. So I heartily welcome all the expertise as well as all the participants to join this and get maximum out of it. And on behalf of whole TechCube section, we would like to thank TechCube Third Project for sponsoring this particular FDP so that we can organize this such kind of activities and get the expertise and the help from all the experts of various domains as well as from prominent institutes of India like NITs and various other research institutes. So I welcome all of you and thanking the whole department mechanical engineering from GC Banswara. Thank you so much. Thank you.
Thank you, sir. Thank you, sir. Now I start now without further ado, let me introduce to our first session expert, Dr. A.E. Sheikh. Sir is currently working as professor in Mechanical Engineering Department of SVNIT Surat. The research interests of Sir include composite material, characterization and machining, CAD and CAE, and reverse engineering. Sir has published more than 83 papers in Indian and international journals as well as in international conferences. Approximately 57 MTech and 13 PhD researchers are guided by Sir. Sir has also been the convener, course coordinator of various seminars, symposium, workshop, conference, STC being organized. Sir has also a book chapter published by him. To add to his honor, Sir has approximately 2 research projects and one patent registered to his name. Apart from this, Sir has also expertise in the administrative responsibilities, like Sir has been the TechCube coordinator and the nodal officer. Although with 27 expert talk in his bag, Sir has presented his skills in his research areas. It's a great honor to have you, sir. So without further ado, I request Sir to start his presentation. Just a small request from all the participants that please put your questions in the chat box. If time permits, the questions will be taken after the presentation. Sir, you can start your presentation.
Thank you very much for giving me this opportunity to be with you and share my work in the domain of composite material with the participant. As the program is on the topic of recent advances in composite material, at present I'm starting with the basics of composite. So whatever is your audience, they will be with the beginning of ABCs of the composite, and later on as the new speakers are coming, they can really enjoy the subject matter. So first I will start with the basics of composites. Good morning all of you.
Good morning, sir.
Yeah, good morning.
Morning, sir.
Good morning, sir.
Good morning, sir.
Yeah, good morning.
Good morning, sir.
Good morning to all of you. Now, starting with the fundamental definition of composites, that we all are aware about the materials. We know what are the homogeneous material, what are the heterogeneous material, which materials have different properties in different direction. So as a engineering graduates, we know that depending upon their characteristics, they exhibit their response for various processes. If you drill homogeneous material, your feeling is something different. If you drill concrete heterogeneous material, your feeling is something different. So therefore, we come with the definition that the composite is a heterogeneous combination of 2 or more materials. Now, these materials normally categorized as reinforced material and matrix material. So if you just see the concrete slab in any building, we see that there are steel material and there is cement and the stone. So we see that concrete itself is a heterogeneous material, but we use a steel. So the purpose of steel is to reinforce the structure. Now, if I come to the general term in composite, in market, we say it is very well known as FRP material. If you go back 30, 40, 50 years back, then all household items were normally of conventional materials like metal, wood, something like that. When plastic was introduced, it was a newer material in that area, in that era. The basic advantage what people can see, that it aesthetic is very good. You don't need to go for a painting. The outer surface is very good. The density of the plastic is very attractive, very light material to replace some conventional materials. Then the process by which plastics can be converted into products are also versatile, available with variety of machines, say injection molding machine, blow molding machine, extrusion process. There are a lot of processes available for processing the plastic. So plastic, when comes into the market, it has tried to capture the entire domain of household product and industrial product by replacing the conventional metals, wood, and the other materials with this advantageous property. The density of any metal, if you take, it comes out to be 7, for MS it is 7.8. Even if you go to aluminum, it is 2.7 gram per centimeter cube. But if you take all plastic materials, it comes around 1.2 to 1.5. So 1/5 is a benefit achieved in terms of the weight, and which was a very attractive property for any product design. If you take a lot of toys, then you can see these plastic materials are used in toys from many years. Now, just for your information, government is giving very good support for developing toy. A lot of schemes are available to support this Indian culture-based development of toys from different materials, which should not be similar to the some dangerous material which may harm to the childs. Then the concept comes into the picture, field. As I discussed the case that the slab material, concrete materials are being filled by steel material. So exactly in the same manner, the concept comes for this FRP. I'm getting some issue. In FRP, the filler material. What can be the best filler? Now, the main issue is the filler material decides the property. Now, if I use a filler material which basically improves the property of plastic, then we can say that it is a reinforced plastic and there is a improvement in the property. But if I use a filler material which does not improve the property and it doesn't give the effect of reinforcement, we see it is a filler material. Now the purpose of filler material may be to reduce the cost of the product, or it may be give you some aesthetic look for the general development of any product. So the reinforced term is only comes into the picture that filler material improves the property. So this is what I just discussed with you, that when plastics are introduced for the purpose of economy, corrosion resistant, aesthetic look, and low weight because of their density. Now in plastic, we already know that we know two types of plastic, thermoplastic plastic and thermosetting plastic. Normally in composite material, in FRP material, we do not use thermoplastics. We normally go for epoxy or polyester, these kind of things, a thermoset plastic. Because the thermoplastic materials are softened with the application of heat, but they also solidify at by the normal cooling at room temperature. But the very good advantage of the thermoplastic based composites or FRPs are they can be recycled. If you see many textile parts developed by the Vadodara based GSFC or something, they use a nylon filled with glass material, and many textile components are produced by this glass filled plastic material. Not only this, but they also use molybdenum disulfide into the nylon, so that engineering plastic nylon is used as a self lubricating material. So you can replace certain parts where you continuously used to feed the oils. That kind of things can be replaced by self lubricating plastic materials. So they are a very good options. But if you take a thermoset, just like epoxy or polyester, they resin material and hardener material react by the chemical reaction, and they get cured. When they get cured, then they are set, and now there is a no softening point by heat, and therefore it is not possible to recycle them, and that product goes as a waste, but it is not biodegradable. So this is a very big limitation of thermoset based composite, that once a component is prepared, then it is not a biodegradable, and you have to look into the other option to use it after the product has completed its life. The mechanical properties is highly affected in case of thermoplastic, but thermosettings are not sensitive to the heat material. The degradation of material at high temperature in thermosetting is a usual process when you make a composite by epoxy or a polyester, and if you go beyond 200, then the blackening of that particular component starts, and even sometime the surface may convert it into the powder form, and then it deteriorates its property. It may not perform as it is designed. As I have already discussed with you that fillers, additives are also fillers. Additives are also filler, but their purpose is something different. So here I have put a few points that additives what you use maybe for the reduction in material cost, for the improvement in performance, then it goes as a filler. It may be used for improving the service life of the end product. It can also be used for achieving ease of processing. Say, I'll just give you an example. Ease of processing means when you go for injection molding and you put a shot of injection plastic into the die, then your material may get jammed into the mold. And therefore, normally people used to apply mold release agent. So sprays are available. If you put that spray into the die surface, then at the end of molding, you will be easily remove the material or say component from the die. So these kind of additives may be used as a ease of processing. Then reduction in processing cost. So even if you take the same case, if it is every time gets jammed into the mold, then the time required for cycle of that particular product will be more. So thereby you will be able to reduce the processing cost, minimizing degradation during the process and use. You might have seen many signboard on the road for advertising purpose. The people use acrylic material for showing the letters. Now what happens after 5 years, 6 years, 10 years, that the finish of that acrylic gets degraded, and if you don't use that UV agent, then because of sunlight, these acrylic surfaces will be become yellowish, and they may become very brittle. So it may happen that just by touching something, it may be having certain damages to the object. So therefore, certain additives are added for improving the life also. The fillers, what we say, which is mainly used to improve the physical property. So last point I have written, to improve the physical improve the physical properties such as tensile strength, modulus, abrasion resistance, and TS strength. But fillers are not always to reduce the material cost. Of course, if the cost of filler is as compared to the bonding material is less, then it can reduce the material cost. And of course, when you add them, it becomes a loading agent. So whatever is the density difference, that will reflect into the product weight as a density of filler separately and density of matrix separately. Now, you might be aware about the high-lem material, which is very useful in engineering industry. This material is available from last 30-40 years. I have seen it long back. Even Westerman table people used to use in industry in 85 to 90 era. When we were working in the industry, we have Westerman table. Westerman table used to give all detail about the section weight and the material data available, processes, indexing, all this. At that time, they also give the detail about the nylon material density, what will be the weight of square feet of nylon plate. Similarly for high-lem plate. So phenolic plastic industry, one is known as bakelite. You might have seen the handle of iron. You might have seen the spherical knob of drilling machine handle. All these products are made by bakelite. So that bakelite is nothing, but it is a phenolic material which we use in our day-to-day life as a product at many places, but we don't realize them that this is made from composites or made from such kind of plastic material. Similarly, high-lem material is nothing but the phenolic resin is being imparted onto the cotton fibers or cotton fabric, and the solid material, solid plate is derived. We say it is a high-lem or phenolic composite. This particular material is very widely used in engineering for creating gears. If one gear is of metal, another gear is used from high-lem. Normally, to reduce the noise, people used to have a nylon gear. But nylon itself has a one disadvantage. Whenever there is a heat generated in that particular assembly, then due to heat, the nylon gets deflected. So in order to avoid that kind of deflection of the tooth of the gear, the people have an alternative to use the high-lem material. So this is a very good option in thermoset category of composite material. What we wish by improvement in the material is the requirement of any product that it should have a low weight, it should have a high strength, good modulus, thermal and or electrical conductivity to be controlled, whether we want or we don't want. So if we don't want, then we will not use any reinforcement of the conductive nature. It should be always by non-conductive reinforcement. But if we wish that the material product developed is a composite and it should conduct, then you can have a reinforcement from metallic element. Similarly, heat
Hello?
distortion, temperature, whatever product
Sir,
you, yes, please.
yes, the screen is not visible actually.
My screen is not visible.
No, no, sir.
Just 1 minute. You did not tell me from the beginning. I was thinking that I have already shared the screen. Now visible?
Yes, sir. Now visible. Yes.
Okay. So I was talking about this requirement for the improvement in the material. So we wish that the improvement by heat distortion, temperature, lower thermal expansion coefficient, and the cost of the product. This is main crux of FRP, what are the merit? That it is a tailor-made design. It is a tailor-made design, so that you can derive the property whatever you wish, and accordingly the proportion of the reinforcement and proportion of the matrix can be decided. Low weight, low thermal expansion, all these points I have already discussed with you. So the merits of FRP, the major is tailor-made design. You can have your own desirable properties of the composite materials. Here just I have just put a table for your comparative ideas. So in the beginning it is not required, but various material and various combination can give you the property, say tensile strength from 45 to 510. So this is how the properties can be changed or can be designed for a material. Now, what are the different thermoset mainly used for the composite materials? Are epoxy. Are you able to see the screen now?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Or I may have a slide like this.
Yes, sir. Visible.
So I think that full screen option is better than this. Okay. So thermosetting, the matrix material mainly used for the composites are epoxy, polyester, phenolics, PEEK, PPS, and similarly for thermoplastic, polyamide, polysulfone, these kinds of material, even nylons, acrylics are also gets extruded. The application of FRP in various sectors, you can see from here that from industry, aerospace, and sports, these are the major area where the composite materials are well known. After 1960, because of the major projects of aerospace, where the cost of placing the object into the space were very costly, and therefore the invention of this composite material was made, and it was fruitful for the aerospace application. Even now all consumer products are also available with the FRP materials. Now, this screen will be able to give you just a judgment that in the aircrafts, the use of aluminium, titanium, and composite, these are the major materials which occupies the area for the material utilization. So these two slides basically give you the idea. Now in composite, the people use the reinforcement, graphite and Kevlar majorly as a reinforcement rather than glass. So glass is normally used for custom products for the general purpose. But the carbon, graphite, Kevlar, these kinds of high strength fibers are mainly used in the aircraft industry because of their high strength property and low weight. Similarly, these FRPs are also extruded to various sections. So just like a PVC pipe and other plastic material, the reinforcement materials are also available from the FRP sections like pipe, round, circular pipe, square pipe, plates, and so on. So even the shafts are being winded. So we say filament winding process is one of the good process for circular object to reinforce or in certain times the pipelines which we put below the ground level and in which the you don't want the corrosion. So under that circumstances, filament winded product either from external surface or from internal surface are being prepared. The demerits of the FRP is welding. See, repairing is a very big issue in FRP. If your flight, if your aircraft is having a bird heat, under the circumstances some crack is formed. Now that component will not perform as it was performing earlier because of the formation of crack. Now it is not the case like a metal that you can do the welding, but it always gives you a long-term damage. So therefore, joining of FRP, so welding and repairing is a big issue in case of FRP. However, there are solutions available. People used to put a patch on it. So a composite patch are being applied onto the damaged surfaces to restrict the growth of the crack. Of course, the environmental condition also makes a difference, that the resin surface gets deteriorated, and if the atmosphere produces the you can say the moisture, that moisture will be absorbed by the fiber and they swell, and the interface gets affected by these kinds of things. And under the circumstances, this you may have a separation at the interface, or you may have a fiber pull out, and you can also have the voids within the material. If you have made it some process, maybe like a hand layup type of process, then you may not be in position to 100% remove the voids. So whenever you cut the section, you will find some blowholes, and that blowholes are allowed up to 1.5% for the design of composite material. But beyond 1.5%, the composite designs are not found to be suitable. Now, as we have already discussed in our lecture, that the basic elements in the composite material, the major elements are fiber, matrix, and interface. There is a lot, I think some disturbance is there. Am I audible?
Yes, sir.
Okay. So the basic elements in FRP is fiber, which we say reinforcing element, matrix element, which basically holds all the fiber in appropriate position, and the third important point is the fiber matrix interface. Wherever the joining takes place at the surface of fiber, we say fiber matrix interface. There is one more term which defines this interface as a 2D, or interface PHASE interface as a 3D. So the bonding, if it is of zero thickness, we say interface, where they just begin to contact, and when there is a interaction takes place between both the surfaces and they form a 3D zone, we say interface, inter PHASE phase. So later on we'll see some slides on that also, that how to check this interface and interface are sound or not. So appropriate characteristics at the interface and their function, both individually and collectively, required for attaining the best properties of the composite. If there is no proper bonding, then the composite strength will be weak. There may be a failure at the interface. So fibers are extremely high tensile strength and moduli, and they are defined as a fiber if they are longer than 100 micrometer and the length to diameter ratio is this greater than 10. So the tensile strength of the fiber is many magnitude greater than the same material in the bulk. The meaning is, if I take the aluminium as a bulk, and if I derive the wire from aluminium, then it is aluminium fiber, then the properties of fiber will be less, will be high as compared to the bulk material, because the thinner the material, the flow will be less. That is a Griffith's law. The thinner the material, it will exhibit the good property because you are removing the flows from the material. So bulk graphite brittle material is having the strength 10,000 pounds per square inch. The commercial graphite fibers are having, see, you can see 800,000. So you can see the improvement in the particular property as a bulk material and as a fiber materials. So basically this slide gives you an idea that when the material is available as a bulk material, it has certain property, but the same material, if it is converted to the fiber, then the properties will be improved tremendously. And the same thing, the Griffith law, we can repeat that the thinner the material, the higher the strength. So fibers are normally having high strength. They are the best reinforcement. They improve the strength, and at the same time they lower the cost of the material also. Not in every case, but whenever the cost of reinforcement is cheaper than the cost of the matrix material, under the circumstances you will get that benefit. The fiber contributes the higher strength and modulus to the composite. This I have just discussed with you. Thinner the fiber gets the more strongness. The demerit of the fiber, that alone cannot take compressive load. It will buckle. So you need a matrix. Without matrix, the fiber will not contribute anything. So the main role of matrix to transmit and distribute the stresses among the individual fibers and to maintain the fiber separated in desired orientation. Say the orientation may be unidirectional, all fibers are available in 0 direction, or all fiber may be available in 45 direction, 45 degree or 90 degree to the testing axis. So that is, we say, desired orientation. In a sample, all fibers should be straight, all fibers should be inclined, or all fibers should be at transverse 90 degree available. So that is a desired orientation. The matrix also provide protection to the fibers from abrasion and from the moisture which is available into environment. So without matrix, the fiber alone has no meaning because it doesn't take any compressive load. And if you want to protect them from the environment, if you want to keep them in specific condition, you need a matrix. So now when you have a matrix, then you will create a boundary at which both the material gets bonded. So here I was talking about these, the matrix provides protection, matrix against the fiber abrasion, against the environmental condition. It also causes the fiber to act as a team because all the fibers are kept in intact position. The maximum service temperature of the composite is limited by the matrix. So whatever is a limitation of matrix, that will be applied to the composite material. Fiber may have any property, but the moment the weakest component gets damaged, the entire composites get damaged. The other desirable feature of matrix are resistance to liquid penetration and freedom from void. So void is say bubbles of air which may form during the process, may be created during the stirring of resin material. Now when you apply them, the boundary which we already discussed is interface. So localized stresses are usually highest at or near the interface. Whenever we design a metal component, we check that if the welding is applied, if it is not failing from welding joint, the component is safe. So exactly the same thing, whenever there is an interface, you need to check the interface. Is there a perfect bonding between the surfaces, of fiber and matrix. If it is there, then your composite is safe. And if it is not there, then the interfacial debonding will be the major cause of the failure of composite material. Now, if there is a issues at interface, the premature failure of composite is also possible. But appropriate chemical and physical feature is also necessary into both the material for a good interface. This interface is necessary for load transfer from matrix to reinforcement. This is a very important statement, because whenever we design, we should take this concept that basically load transfer is not from fiber to matrix, but it is from matrix to fiber. Now, this interface can be improved by using appropriate coupling agent. So the interfacial bond must resist the stresses due to differential thermal expansion of fiber and matrix, shrinkage of the resin during the curing, and in protecting the fibers. Even you might have seen the bridge. So after a certain span of bridge, there is a gap of say 1 inch or 1.5 inch. It takes the care for the environmental condition that during the winter season material gets shrink, and during the hot season it gets expanded. Now, because of that, if it is a one piece, then there may be an option that the cracks may form. Even if you might have seen on the terrace, the tiles gets be debonded in the hot condition because of the thermal expansion. Material get expanded. So you can apply the appropriate coupling agent, which will improve the interfacial condition. Now, this bonding is a very important. Say the failure at interface should always be avoided. And before I go for the manufacturing processes, I'll just give you one more slide. This one. Interface and interface. Now here you will be able to understand the difference, that the interface is defined as a two-dimensional border between fiber and interface, or fiber and matrix, in the cases where no interface is considered to be present. It means three-dimensional region. If it is not formed between fiber and surface, then there will be a direct contact between fiber and surface. We say that boundary as an interface. But the interface, PHASE, is defined as a three-dimensional region between fiber and bulk matrix with a different morphology, chemical composition, and mechanical properties compared to both fiber and matrix. In case of metal, we say alloying. When we mix the material, two different materials, then in aluminium, if we add something, chromium or something, then the alloying takes place. And that alloy is having some different property, which is not matching with a part A or part B. So exactly in the same manner, the three-dimensional region formed between fiber and matrix, we say interface. So that is a 3D region between fiber and bulk matrix. It has a different morphology, it has a different chemical composition, and it has a different mechanical property as compared to both fiber and matrix. And this interface or interface, both are important to be to design any composite material, because if at interface there is a debonding takes place, then whatever strength material you select, either carbon, boron, it has no meaning, because the interfacial failure will create debonding between the different layers, and that should not be the case with any composite material. So here, if we see that the how to measure this strength, bond strength, there is a perfect bonding between fiber and matrix is generated or not. So that can be taken care by using the pull out test. So those who are a beginner, for them, this property, to understand this property is very important, that what is the bonding between the fiber and matrix. So for that, the people used to go for a pull out test. So normally we go for tensile test or a compression test or a shear test, but whenever we talk about the composite material, then we should always think that initially at interface, what is the bonding between fiber and matrix. So in many times in a live class, I used to give the example of this bond material, quick fix, quick bond, that when you join any thing, say if you want to join anything to anything, then this quick fix, quick bond, fabi bond, these kind of materials are available. You just put a drop and try to stick them. So there also, if you see that on the box, it is written that you can join anything to anything, but except broken heart. So if you see, normally in class, I used to give this something, people may have a joke on it, that they may laugh on it, anything to anything except broken heart. Now here, I would like to explain what is a broken heart. That compatibility of the material is very important. Compatibility between the material is very important. I think there is some properties there. I'll just show you this one, wettability. See this. Now this is purely depending on the material itself. So material A and material B, if you apply the resin to any fiber, maybe carbon, maybe boron, maybe graphite, but if that particular resin material is not able to wet it properly, then you will have a dry region into the composite material when you cut it. And whenever there is a dry region, then you cannot design the proper composite. It is a very big demerit for the composite material. And therefore, the surface what you are using as an interface will not be appropriate. So interfacial bonding says once the matrix has wet the reinforcement and is therefore in intimate contact with the reinforcement, bonding will occur. So this is very important. You need to read this initial line. Once the matrix has wet the reinforcement and is therefore in intimate contact with the reinforcement, bonding will occur. If bonding in design of composite material, there is a first assumption that there is a perfect bonding between fiber and material, then only the rule of mixture will be applied. We'll see later on what is the rule of mixture. But whenever you would like to see that the rule of mixture is applied, the first assumption that there is a perfect bonding between fiber and matrix. So here I'm same thing I'm narrating with different definitions, that it is an interfacial bonding. The matrix should be able to wet the fiber. If it is perfectly wetting the fiber, then there is an intimate contact, perfect bonding, and then the material is perfectly designed. Now the number of different types of bonds may be formed when you apply this condition. So we say interfacial bonding, say mechanical bonding. Say you know that on a bike accelerator there is a serration, mechanical serration. Why there is a mechanical serration? So that our hand can properly grip it. Our hand can properly grip it. If our hand is not able to properly grip that acceleration, there may be slippage. Now, in order to avoid that kind of slippage, the surface should be rough. It should not be smooth. It should not be finished one. It should have irregularity so that mechanical anchorage takes place. This mechanical anchoring at the two surfaces. Hello, any issue? Are you able to listen me?
Yes,
Am I
sir.
audible?
Yes, sir. Yes, sir.
Yes, sir.
So mechanical bonding is best thing, and therefore lot of research paper you will find on surface treatment for getting the better property of composite material. It is nothing but on a surface of fiber, we are basically removing the finishing and we are creating the etching surface so that this mechanical anchoring can be generated between the resin and the fiber material. Similarly, you can have an electrostatic bonding, you can have a chemical bonding. So all these kinds of bondings are possible, reaction bonding. So better understanding of the interrelationship between fiber, interface and matrix will lead to the concept of interface, that is a three-dimensional region between fiber and material with different mechanical properties. And if you see the many research paper, the people are working on the interface, they believe that whenever you bond material A with material B, if there is a good compatibility between them, then this third dimensional interface region will be generated and it will be responsible for the good design, that it will give a proper bonding. And the assumption what normally people take into the case of rule of mixture, there is a perfect bonding between fiber and matrix can be attained. Now this term also we have seen, coupling agents. There are certain elements which try to become mediator and they try to improve the bonding by using coupling agents. So this is one of the examples that coupling agents can be applied onto the fiber surface, or there may be you can use a treatment to the surface so that it becomes a rough surface and it becomes readily available to be wetted by the resin materials. Now the fiber matrix adhesion can be tested under this pull out fiber fragmentation test. You can have one test like this. In a matrix, you will have a single fiber, and you should try to test it for unidirectional tensile strength. You can also go for short beam shear, off axis, or this impact kind of things. So all these tests are possible. Then for a pull out test, you have an option like micro indentation test or a meso indentation test. You can see here the arrow which has been shown, which is trying to push the fiber to be out from matrix. So these kind of tests will give you the property what is happening at the interface. Similarly, you can see here cylindrical matrix is assumed, and in the center the fiber is being placed over here as a black color one. Now this is a matrix, and if you try to pull this, then this particular surface here, this surface will give a resistance, and this resistance is mainly due to interfacial property between fiber and matrix. So if you are able to remove the fiber easily, then the design of composite is not proper. But if it gives a lot of resistance and then after certain value of load it comes out, you can say that yes, there is the interface exists and it will give a good strength to the composite material. And there are various formulas are available whereby you will be able to evaluate the interfacial shear stress and many more property. Here I'll just show you this one example with our own experimental work, that you may have a case like this. Force A. Initially, the bonding will try to keep the internal fiber up to some extent, and then suddenly it will fail. So you will have a failure like this. The second case, that gradually it will give a bonding up to certain limit, and then it will try to give a resistance and then slowly it will fail. So basically the interface is giving resistance in failure. And the third one, C, this is the best case, that if you have prepared the staircase kind of things onto the surface of the fiber, then at every instant it will give you, this is a bonding, then it will give resistance by mechanical anchoring. So that is why we used to prepare the surfaces of the fiber, and by using a rough surface you can increase the interfacial strength tremendously, maybe from basic bonding to 3 times, 4 times, 5 times, depending upon what kind of mechanical engagement you have been able to generate it. So here I will just show you one example. So how we prepare this test in laboratory. This is just a theoretical solid modeling CAD model to express that this is my die under which I put this pipe, this rod, and then from here I feed it the material, so that what happens, that you will be able to feed the material from here, and in the surface you will see the component like this. See, this is a polymer, and in a polymer rod is inserted. Now I take up this case as a single fiber embedded into the matrix material, and the surface of this particular reinforcement is having various roughnesses. So for that we have taken these cases: 0.5 micron, 0.7 micron, 0.9 micron. What is that? That this rod is initially rubbed with the emery paper, which has a different roughness. So depending upon that roughness, we could able to measure this 0.5 micron, 0.7 micron, 0.9 micron. So various roughnesses are being created manually onto it, and accordingly these specimens are being prepared. Now when these specimens are prepared, then they have been taken to the tensometer. For this particular jaw is used to put the polymeric portion into it, and this rod is being taken to the another jaw of the machine so that it can apply the pull. Now this tensometer what we use into the laboratory is of the capacity of 2 ton loading capacity during the tensile, and it has been applied to pull out this completely. Now this pull out gives you the idea that at interface what is strength, what is the bonding between fiber and matrix, because we presume that there is a perfect bonding between fiber and matrix, means there will theoretically there will be no failure at the surface. Either there will be matrix fail or there will be a fiber fail, but in real life it may not happen. So that is why to evaluate this we take up this case to measure the bonding strength by pull out test. And I think you may be able to see this yellow color graph. So this is basically load versus displacement for 0.5 micron roughness for a pull out test specimen. Similarly, this is for 0.7 micron roughness. You can see this zigzag. Now this zigzag means whatever emery paper you have applied onto the road, every instance you will feel that there is a resistance. That is why this peak and valley has happened. Then after a certain period, it has fall down. Similarly here 0.9, see it has moved like this up to here and sudden fail. So this is how you will be able to see this failure results. I'll just see the table. Now see, when there was a 0.5 uh, applied micron to 35, when you take gone for a big size of emery paper, more roughness, then you will get this reading. So 0.5, 0.7, 0.9, and the load required to pull the rod from polymeric ring, that is increasing. So second criteria was varying embedded length. Now if you see this sample, now the sample which is this particular rod which is inserted into it was having a varying length. So what that varying length? That 4 mm, 7 mm and 10 mm. So into the cylindrical object of a polymer, polyester, we inserted the rod for 4 millimeter depth, for 7 millimeter depth and for 10 millimeter depth. Now basically by increasing this embedment length, we provide more area of contact between fiber and matrix. So interface surfaces are being increased by this embedment length. Now, if you increase the interface length, then what happens to 7 mm, 10 mm, and 4 mm? Which by results you may be able to see that for a 4 mm the load required 39, for a 7 mm 49, for a 10 mm 58.8. So basically this gives you an idea that if you take the fiber and matrix, what are the different parameters, what contact area you give between the fiber and matrix for bonding, accordingly the strength will be verified. So even if we consider, when we take the theoretical case of anything by tackling by rule of mixture, we say VF, EF, VM, EM, volume fraction of fiber, volume fraction of matrix, and what is the property of fiber, what is the property of matrix. But at that time, certain other parameters are also equally important for designing the material, that we have seen by this pull out test, that if the surface area is improved, and that is why now people are using the nanotube, carbon nanotube insertion into the matrix, because at the interface they give tremendous area. 1% of carbon nanotube can increase the percentage of interfacial area into a numerous value. So thereby the property can be improved by incorporating the carbon nanotube. Now, the same thing what I am showing you here as an experimental case, I have simulated also it by the FEM approach. So we just make a quarter rod, 1/4 area of the rod, and here the cavity is being created for inserting the rod. Now you can see this. This is representing embedded length. This is representing, you can have 4 mm, 7 mm, 10 mm. And then on this surface, this is a smooth surface. There is no serration. There is purely finished. So it will not resist anything for a zigzag manner. Purely bonding will be exhibited by this. But later on, we give a serration groove onto the object. This is a serration provided on it. So number of serration represent your emery paper by 0.5 micron, 0.7 micron, 0.9 micron, and you can see here the slits are being cut. Now this red color thing is a matrix material, and yellow color is a rod material which we considered as a reinforcing rod, and this is the matrix material. Then we go for the analysis using Proe Mechanica. Of course, this is not a good software, appropriate software for the highly computational aspect, but for preliminary observation, you can use this one. Otherwise, you can go for ANSYS, Abacus, where you can consider the more detail and more options for defining the composites. So we go for varying this. We define the one material, we define the second material, we define the boundary condition, we define the loading condition, meshing, everything's were defined. The faces were also defined for defining degree of freedom to be 0. That particular faces are fixed one. And then the load conditions are also given to pull the road. And what we have seen into the tensometer case, the same simulated results are being applied over here. And the post-processing result, we can see some displacement, some stresses. So all these results we will be able to note down from here. And you can see that this is a pull in this direction, and this is the amount of stresses generated into the fiber body and into the matrix body. So here this is a displacement results. So we compare that the surface roughness variation by 0.5 micrometer, 0.7. This we measured by Mikyutoyo surface roughness measurement on the road. Then we see what is the maximum load, we can see what is the displacement, we can see the same thing we see in the simulation also, and what is the percentage deviation we find into the result between a simulated result and into the actual measurement result. So all this result we find in the case of surface roughness 5 to 6.7, and similarly for embedded length also, when we take the different embedded length 4, 7, 10, the deviation is in the range of 7 to 8.16. So this is how you can simulate also by the pull out test for any composite material and any design which you need to take up for designing the composites. Now I'm coming back to my original slide where I have started with the composite. It has a 3 element: fiber, matrix, and interface. I talk a lot of things on interface because it is a very important parameter. Without that, composite does not exist. And many of you are a faculty member or maybe a research scholars, those who are doing some research work, then unless and until you don't focus on interface, it is very difficult to go for the detailed research into the composite materials. The manufacturing process normally we apply for developing the composite material specimen. If we don't have the good facility, you can take a plate, you can just put a plastic material, apply the glass mat, spray the resin, and again put a plastic and apply the roller on it, so that you will be able to fabricate the composite material. So this is a very preliminary process what normally people are using even in day-to-day routine. Also, when you go to some fabricator, they normally go for hand layup technique only. They use glass mat and they spray the resin. After spraying the resin, they apply roller to remove the void content from the material. The second one, you can use a spray up on the mold. You can first put the your you can say spray mold release spray or a plastic film, and then using this gun you can spray the chopper fiber with resin mixture, and they will be deposited onto that particular surface. After curing, you can remove it. Similarly, you can have a compression molding. For that you require match mold. You may have some male and female kind of toolings to give the appropriate shape to your component. Similarly, you can have resin injection. In the closed mold, you can inject the resin, and the process is known as resin injection molding. Similarly, pultrusion, if you want to create a continuous shape, say rod, then you should have a die. In the die, you should have a cross section like a circular one. Then from one end, you can insert the fibers which are already wetted into the resin. Then puller will pull it, and in the die you will apply the sufficient amount of temperature by heating it, so that the resin gets cured. Say you are using a polyester resin, elevate the temperature of the die section such that it reaches to its kick-off point and it gets cured. You try to keep it into the die for a certain period. That post-processing curing is also allowed during the curing process, so that when you remove it, it is a perfectly cured. No doubt, the curing process is a continuous. Even after it is cured from mold, it may take curing continuously, maybe a day or days or weeks. It is a continuous process. Similarly, you can also have sheet metal compound and bulk metal compound, sheet material compound and bulk material compound, where you can have a charge. That is basically you are chopping the fiber into small pieces, you are mixing it with the resin, and then you are applying it. So whether you are creating a sheet between the two plastic sheets, or you directly apply it onto the mold by using a BMC process, and then it will be creating a composite material. Similarly, if you want to create a circular object, then on a mandrel you need to wound it. So the process is known as a filament winding. So all fibers are first taken into resin bath for wetting the fiber, and the guides are giving to appropriate direction for winding, maybe 45 plus or minus 45, like that, both direction, so that uniformity in the material will be applied. So filament winding is a good process for a cylindrical object. The theoretical aspect which we consider in designing is nothing but micromechanics. So micromechanics basically design that how much percentage you are trying to take fiber, how much percentage you are trying to take the matrix material, and what will be its end property. So basically, composite property is a response you are interested to have, and for that you must know the constituent property. Suppose you are taking carbon fiber and at the same time you are bonding them with epoxy, so you must know what is the property of carbon fiber and what is the property of resin what you are using epoxy. So constituents material property, you can have EF, EM. EF means fiber elastic modulus of fiber, EM elastic modulus of matrix material. Then macromechanics is nothing, it is an analytical method to predict what will be the composite property, what will be its strength, what will be its elastic